Hello everyone, welcome back to our class, Advanced Thermodynamics and Heat Transfer. Chapter 11, Mass Transfer. Let's continuously discuss Section 2, Convection Mass Transfer. I said mass transfer is very similar to heat transfer. The convection will occur between a moving fluid and a solid surface when their molar concentration is not the same. Mass transfer is very similar to the heat transfer I said. In this picture, if Ca is not same, CAS, convection will happen. As we know, velocity boundary layer will be produced when the free stream flows from the plate. Here, plate the area is AS. Very long distance, the flow rate is U infinite. For heat transfer, a temperature boundary layer will be produced when the free stream flows from the plate with different temperature, like this. The Ts is not same as T infinite. So a layer, heat transfer layer will be happen. Okay, when free stream, including the mixture of A and the B, flows like this from the plate with different molar concentration A, the concentration boundary layer will be produced like this. Very long distance is A and B. The surface only A. So the concentration is different. So concentration layer will be happened. We do some comparison between heat transfer and mass transfer. We find the layer is very similar. We use the Newton's law of cooling to calculate the heat transfer, the convection heat transfer. Q equals HA times the temperature difference. In mass transfer, we use another equation to calculation the mass transfer flux. NAS equals HM times A times the concentration difference. CAS minus CA infinite. Using the Fick's law to the boundary layer, very similar to the convection heat transfer. We are interested in the molar flux of species A and Na. We obtained Na equals minus DAB partial Ca partial Y. Here, DAB is the boundary diffusion coefficient. This equation we have learned in the diffusion mass transfer. Near to the plate, Y equals 0, the fluid is stopped because of the friction. There is no convection, only diffusion, so the molar flux NAS equals minus DAB partial Ca partial Y at Y equals 0, like this, very close to the plate, because very close to the plate, the flow rate is zero, only diffusion. The mass transfer from a solid surface of area A at a molar concentration Ca to a fluid of Ca is given by Na equals Hm, A times concentration difference. Hm is the convection mass transfer coefficient. Na is always plus. Its unit is kilomoles per second per meters. It is a flux. For different position on the surface, certainly NaHM certainly is variation because the flow situation and density distribution is not same in different position point. For whole surface, certainly we calculate Na, we should use average coefficient Hm. If the concentration is uniform on the surface of the solid, because the surface concentration is uniform, so CAS minus CA infinite can move to outside of the integration. Okay, the average convection coefficient Hm is defined for whole surface. Obviously, the relationship between the local coefficient and average coefficient is given by this equation. The average mass transfer coefficient equals 1 over As integration on As on surface Hm times dA. In a word, for whole surface, the mass transfer will be calculated by this equation. Na is average Hm As times concentration difference. We use this equation to calculate. Very similar to the convection heat transfer. Okay, the mass transfer equation certainly can also be expressed as mass flux, like this. Na equals Hm As low As minus low A infinite. Low is the mass density of A species. If the species A is ideal gas, near to the wall, the molar concentration can be expressed by this equation. CAS equals P saturation Ts over RTS. R is universal gas constant. Okay, we can do some comparison about velocity and mass transfer boundary layer. Diffusion in the velocity boundary layer, certainly we can draw the picture like this, similar to the convection velocity boundary layer. Here, the boundary layer length will increase with the x. So you can find very similar to the velocity boundary layer. Concentration boundary layer, if we understand, certainly we can build some equation, boundary layer equation for laminar flow. Also is similar to the convection equation, heat transfer equation. Very similar. We do the same thing, same way. So this is conservation equation. We obtain like this. This equation: U partial Ca partial x plus V partial Ca partial y equals dAb partial Ca power second over partial y power second. Species conservation equation. Similar mass conservation equation. Similar energy conservation equation. Similarly, we can let the equation normalized order Ca star equals Ca minus Cas over Ca infinite minus Cas. Dimensionless concentration, we think Ca star. Do the same way as the convection heat transfer. Also, we obtained U star partial CA star partial X star plus V star C partial CA star over partial Y star equals 1 over Reynolds number. Here SC is Smith number. It's not the same as the heat transfer. Heat transfer is Planck number. Here is Smith number times partial CA star power second over partial Y star power second. These two equation is boundary layer, boundary conditions. Smith number is mu over DAB. It's called Smith number. Similar to the thermal boundary layer, diffusion equation can be get the general solution. The solution, we can guess the solution like this. There is relation to X star, Y star, Reynolds number, Smith number, and pressure gradient. Hence, we may define a dependent dimensionless parameter termed the Sherwood number. Sherwood number is Hm times L over DAB. Very similar to Lucet number. Sherwood number is Hm times L over DAB. Very similar to the Lucet number. This parameter is equal to the dimensionless concentration gradient at the surface. Okay, for corroborate geometry, Sherwood number equals function of X star, Reynolds star, and Smith star. So Sherwood number is to the concentration boundary layer, what the Lucet number is to the thermal boundary layer. As for the Lucet number, it is also possible to work with an average Sherwood number. That depends on only Reynolds number and Smith number. So Sherwood number, the average, equals the mass transfer coefficient average times L over DAB. Is a function of Reynolds number and Smith number. So we can use the heat transfer equation similar to the mass transfer. Here we discuss physical interpretation of dimensionless parameters. Planck number strongly influence the relative growth of the velocity and thermal boundary layers. For laminar boundary layers, we know delta. Delta is velocity boundary layer over delta T. Delta is thermal layer boundary layer equals Planck number power nth. N always is plus. Okay. Similarly, the Smith number provides a measure of relative effectiveness of momentum and mass transport by diffusion in the velocity and concentration boundary layers. So delta over delta C. Delta C means mass transfer layer, the thickness, equals Smith number power nth. So here is the relative thickness. We defined another number is Lewis number equals A over DAB. It's called Lewis number. Is Smith number over Planck number. Here A is the thermal diffusivity. A equals lambda over rho Cp. Lewis number is relevant to any situation involving simultaneous heat and mass transfer by convection. Generally, delta T over delta C is about Lewis number power nth. In many cases, n is 1 over 3. It's 1 over 3. It's very small. It's not so big. Okay, next several page we will discuss the mass transfer in external flow and internal flow. Just several examples. most cases we use the empiric relationships. One is laminar flow over an isothermal plate. Isothermal plate means the temperature is constant. It's the same, it's uniform. Similar to solve the heat transfer boundary layer equation, we can obtain the relationships similar to the heat transfer. Show the number x equals hmx times x divide dAB equals 0.332 Reynolds number power half times Smith number power 1/3. The condition is Smith number larger than 0.6. So for isothermal plate, laminar flow, the mass transfer, we can use this empiric equation to calculate. For external flow. For hold plate, the Schroeder number equals Hm average times x divide dAB equals 0.664 Reynolds number times Smith number. Reynolds number power half. Smith number power third. So this equation we can use to calculate whole plate the mass transfer. The second problem is turbulent flow over an isothermal plate. In this case, we use these empiric equations to calculate. Salt number equals 0.0296 Reynolds number power 4/5. Smith number power third, power 1/3. Smith number, the range is 0.6 to 300. In this case, velocity boundary layer equals thermal boundary layer, and the mass transfer boundary layer, the thickness is similar. Thank you.